Hello. Hello students, good morning everyone and welcome to Vedantu J English, and today we are going to do questions of solution chapter. So guys, let me know in the chat box if I am clearly visible and audible to all of you so that we can start with the questions of solution chapter. Right everybody? Everyone, and where are the students? Everybody join in fast. Join in fast. So, let's talk about solution chapter. So, we know that from here, Raoult's law, Henry's law, colligative property. These are the topics from where the questions are asked, right? So, let's talk about, uh, we'll talk about medium questions. You have to tell me also whether you will be able to solve that question or not, right? So, if I see this here, first question on your screen is a standard solution of HCl3 has vapor pressure 7.17.2 while the pure water vapor pressure is this. Okay, this is like vapor pressure of pure solvent and this is the vapor pressure of solution. So this we can say this is P naught, this is PS, right? This value is nothing but this is PS, right? That is vapor pressure of solution, and this is the vapor pressure of pure water, that is the solvent, that is P naught. Solubility product you have to find it out of HCl3 at it. Okay, so we know that if I talk about HCl3, this is X3 negative plus 3 or X3 positive plus 3 of Cl negative, right? And from ionic equilibrium, how to calculate the value of Ksp? We know Ksp is equals to this stoichiometry raised to power stoichiometry, this is 1 raised to power 1, 3 raised to power 3, solubility raised to power 3 plus 1, that is 4. So Ksp value is nothing but 3 into 3 is 9, 19, 27, 27 S and 4. Now that means all you have to find out is for Ksp you have to find out the value of solubility here, right? Then you can easily find out the value of this, right? Now to find out the value of solubility, right, that means we have to find out the value of concentration here, right? So concentration of HCl3 will give you the concentration of X3 positive, that is the concentration of this. Now if you see this here, in this case a saturated solution of this, and they are saying molality is equals to molarity, and we know that somehow from this we are clear now which colligative property to use here, right? At first instant it might feel that this is a question of ionic equilibrium, but only this part is from ionic equilibrium, other thing is from solution chapter. These are mixed questions that they can ask you, right? So if you see this here, this is going to be, we are going to apply lowering of relative lowering of vapor pressure, that is directly proportional to mole fraction of solute, right? So if you see this here, it is going to be one thing I am going to do here, right? One thing I am going to do here, that if you see how you determine this formula, the major part is, ma'am, how can you just write this formula in terms of molarity or molality? Let's talk about that. If you know P naught minus Ps divided by Ps is equals to want her factor, number of moles of solute by number of moles of solvent. Now we have multiplied it and divided by molar mass of the solvent. Now if you see this over here, what is molality? What is molality? Molality is nothing but it is number of moles of solute divided by weight of solvent. If it is in grams, it will be multiplied by 1000. Can I say this is number of moles of solute by number of moles of solvent? How I am doing that? If I do this thing, if I divide this by mass of solvent and multiply this by mass of solvent, then this is number of moles. Okay, so this will become number of moles of solute divided by number of moles of solvent. Oh, only audio is coming. Okay, now hello. Now is it fine? Oh, chalo, I'll just do this again. Okay, I'll just do this again. OMG, we were at this point, huh? Chalo, I'll just do this again. I'll just show you this again. Tell me. Yeah, I just saw it. Okay, now see what we were saying. They have asked you solubility product, and that the simple trick is stoichiometry raised to power stoichiometry raised to power stoichiometry, solubility raised to power 3 plus 1. Addition of solubility, addition of stoichiometry, and this is the overall KSP value that you will have. Right? Now, this overall KSP value, is it not in. Yeah, wait a minute. Hello. What's happening, guys? Is it fine now? Is it fine now? Yes, is it fine, everybody? Tell me in the chat box. Tell me in the chat box. Now, is it fine? Shall I do the question? Now, is it fine, everybody? Yes. Okay, shall I do the question? Yes. Okay. Now KSP value, you got it now, how we solved it. This is the part of ionic equilibrium. But how to calculate solubility, that we will see from solution chapter. Now here P0 and PS is given to you, so you can apply relative lowering of vapor pressure here. Now let's calculate this over here. To answer, we know that relative lowering, this is relative lowering in vapor pressure, that is equals to a Van Hoff factor into mole fraction of solute. Mole fraction of solute is nothing but number of moles of solute by total moles. Now solute moles are very less in comparison to solvent, so that's why we write it as number of moles of solute by number of moles of solvent. Now what we need to understand is what is molality. Molality is number of moles of solute divided by divided by weight of solvent, right, multiplied by 1000 if this weight is in grams, right, if this weight is in grams. Now see one thing, if I multiply and divide this by molar mass, right, if I multiply and divide this by molar mass, this is weight of solvent, this is, let's say, molar mass of solvent, and this is molar mass of solvent. This whole part is multiplied by 1000. Now what is this? This is nothing but this is number of moles of solvent. So can I write molality is equals to, this is number of moles of solute divided by number of moles of solvent multiplied by 1000 divided by molar mass of solvent. Can I say this is another way of writing molality? So can I put this here, number of moles of solute, solvent, molar mass, and this 1000. This is molality. This is molality. So molality multiplied by molar mass of solvent divided by 1000 will be left behind. Now this is the formula that you have in terms of molality, right? Now if you see, you have the molar mass of solvent. Solvent is water. We know its molar mass is 18, right? We know what is Van Hoff factor, right? Here, because we are assuming it to be complete dissociation, that is the reason Van Hoff factor is going to be, if alpha is 1 here, right, then we are going to assume it to be 4, right? Okay, that is going to be 4 here, right? This we know, this we know, this we know, this is given. If you see this over here, P0 is given, PS is given, everything is given here, right? Now we will solve the value of molality from here, right? So molality, you will put all the values. This want Hoff factor, you will put it as 1. This is 18, right? This value of P naught, PS, you have put everything here. And after that, you get the value of molality as 0.04. Now molality and molarity are same, and I told you that solubility is nothing but it is molality only, right? If you see this here, concentration is only solubility that you take. It is mole per liter only that you put here in the value of solubility, right? So molality is equals to molarity, that is given in the question, and molarity is what we are saying solubility. So just put it here, 27 into, this is KSP is equals to 27 into 0.04 raised to power 4, and that will give you your answer here, right? Okay, is that clear? Molarity is the molar solubility here, right? Okay, tell me. It will be 2, but whether the number of ions determine the Van Hoff factor. Uh, Ma'am, for complete dissociation, normally, no, normally it's, we don't say normally it's 2. When there is complete dissociation, Van Hoff factor is equals to number of ions, right? Here, complete dissociation is there. Alpha is equals to 1. And that is the reason here, how many ions it is getting dissociated to? 3 plus 1, 4. That is why we have taken Van Hoff factor as 4, right? Tell me, is that clear, everybody? Is that clear? Do let me know in the chat box. Next question is, now these things are given to you, and that is 4 colligative properties that you have: elevation, osmotic pressure, relative lowering, depression. Now based on this, you have to tell that whether all of these things, which is correct or which is not correct. Okay, options are given to you. If you see, all of them are P, all of them are colligative properties, so all of them are definitely P. So I'll just eliminate where all of them are not P. AP, BP, here also BP is there, CP is also there in everyone, DP is also there in everything, right? Now let's calculate the other thing, osmotic pressure, right? If you talk about osmotic pressure, that is firstly I'll talk about elevation and boiling point, that is elliptioscopic constant. It is related to in Kp. In a boiling point, elevation and boiling point, you have Kb, that is elliptioscopic constant, right? So here A is also Q. A is also Q, but here A is not also equal to Q. So in all these cases, A is also Q. So this will be the answer. Now let's see. What about others? Osmotic pressure is related to Berkeley-Hartley method. That's how you calculate the osmotic pressure, right? Then this B is equals to R here. So B is R, B is not R here. So this will be eliminated. B is also not R. B is S here. So this will also be eliminated. So answer is A is the correct answer. What about C? We can see relative lowering in vapor pressure. That is Oswald and Walker method, right? And depression in freezing point is just colligative property here, right? So we can say that definitely A is the correct answer here, because C is equals to P and S. P is colligative property and this is Oswald method, and D is equals to only colligative property. There is no other match that you have for D. So answer is going to be A is the correct answer here, right? Okay. Now next question that you have here is, let's talk about this. Now next question, guys, everybody, let's talk about this. Column 1, this is column 2. Now in this case, what you have, uh, like this can be separated by fractional distillation, maximum boiling azeotrope, minimum boiling azeotrope. These things are given to you. So these, it's like it's an advanced version of telling that which is positive deviation, which is negative deviation, right? Okay. So if you see this here, this is ideal solution, है ना? This is ideal solution. This is also ideal solution. Then you have acetone and chloroform, and here you have ethanol and water. Now understand one thing, whenever you talk about positive deviation, whenever you talk about positive deviation, in positive deviation, right, interaction should be decreasing, right? Interactions should decrease, right? Only then it is positive deviation. And in the negative deviation, interactions should increase. Okay, interactions you will see are increasing. So can you see this over here, that acetone and chloroform and ethanol and water you have, where interaction is decreasing, where interaction is increasing, right? Okay. Ma'am, if cryoscopic constant is given, then the part that is related to cryoscopic constant, you will mark, uh, let's say here cryoscopic constant is given, right? Let's say here cryoscopic constant is given. Then you will mark this particular depression in freezing point as P, and let's say PQRS. T is also, let's say T is cryoscopic constant. Then you will mark this as P and T. Okay, so you just have to see what is related to what, and according to you will mark it, right? Okay, now see one thing here, right? This is negative deviation, it is increasing. And one more thing guys, one more thing, in the positive deviation, boiling point vapor pressure is decreasing. That means vapor pressure is increasing. That is means boiling point will decrease, so it will be minimum boiling azeotrope, right? This is maximum boiling azeotrope. So all you have to do is you have to tell which one is positive deviation, which one is negative deviation. Yes, everybody, do let me know in the chat box if that is clear to all of you or not. Right, students? Yes, students, do let me know. Okay, now we'll mark it, wait a minute, let me see the options here, right? If you see, it is A is given PPPPP. That means A, so we don't have to even see, right? A is given PPPPP. That is the ideal equation, that is the ideal solution, right? Ideal solution can be separated by fractional distillation, or it cannot be separated by fractional distillation. So ideal solutions can be separated by the fractional distillation, right? Okay, because they are not azeotropes. Whenever a solution is non-ideal, it is either, see, simple thing is, whenever a solution is non-ideal, either it's positive deviated or it's negative deviated. Positive deviated or negative deviated will be azeotropes. That means they will form a boiling point in which they both are boiling, right? So for azeotropes, there is a constant boiling point, right? For both, for the solution, it's not the individual, so that's why it is difficult to separate them from the by the fractional distillation, right? Now chlorobenzene and bromobenzene is also P. So let's see this here. Chlorobenzene and bromobenzene is also P, so C is also P, right? So you can see this here, A is P and C is P is in this case, A is P and C is P in this case. In other cases, both of them are not P. No, it's here also it is A is P and this is also C is P. So this one is eliminated. We have to now see whether B is Q or B is S or R, or it is only R. Okay? Let's see. Now if you see this here, right, acetone and chloroform. Acetone is what? Acetone is CH3, C double bond O, CH3. This is acetone. Chloroform is CHCl3, right? So what will happen in this case? In the acetone, there is not as such interactions here. In ethanol and water, though, we can see interactions will decrease. In this case, interactions will increase, so we can say negative deviation. Negative deviation means maximum boiling azeotrope. And R, though, definitely will be there because these are non-ideal solutions, so they will not be because they are azeotropes. Non-ideal means they are azeotropes. Either it can be maximum boiling or minimum boiling azeotropes. Azeotropes have a solution boiling point, so you can't fractional distillation is based on difference in the boiling point. So if boiling point is same only in azeotrope, that is the definition of azeotrope. Now that boiling point becomes same. Now that means azeotropes cannot be separated by fractional distillation. So B's definitely are, and D's also are. B's also are definitely, and D's also are definitely. But in case of B, you will have maximum boiling azeotrope because here interactions are increasing. In this case, interactions are decreasing, right? And that is why it is, when interaction is decreasing, it is minimum boiling azeotrope. So here it will be Q and here it will be S. So here it is RQ, here this is RS. So you can see RQ is here and this is RS is here. So answer will be A is the correct answer here. Is that clear, everybody? A is the correct answer here. Okay, that's how you tell this. So that was a very important question based on examples. This was the example of positive negative deviation ideal solution, but directly it's not just like positive deviation negative deviation. It is telling you so many things. It is telling you how you can tell this based on fractional distillation, how you will tell whether it's minimum boiling azeotrope or maximum boiling azeotrope, and what are the properties of this azeotrope, that azeotropes cannot be separated by fractional distillation, but ideal solutions can be separated by the fractional distillation, right? Next question is, at 10 degrees Celsius the osmotic pressure. Now guys, everybody see this question over here. At 10 degrees Celsius, the osmotic pressure of urea is 500. The solution is diluted and the temperature is raised to this when the osmotic pressure is this. Determine the extent of dilution. See, osmotic pressure is given to you. They are saying extent of dilution. Pi is equals to CRT. So what you are changing here? You are changing osmotic pressure when the concentration is 1, temperature is also what you are changing, right? So I can take this as, of urea solution is this, the solution is diluted, on dilution this is this. So let's say this is T1, osmotic pressure of this much. This is pi 1, the solution is diluted at a temperature is, this is T2 and the pressure is pi 2. Okay, determine the extent of dilution. So what you can do here, you can say pi 1 is equals to, you can take the ratio here. This is C1R T1, this is C2R T2. Now you have to find the relation between C1 and C2, right? Temperature both are given to you, put it in Kelvin here, right? And pi 1 and pi 2 is also given to you. Solve this value and find out the relation of C1 and C2, right? So if you see this here again, for the urea solution, we have taken this thing here, right? So take the ratio here, solve the values, put the values in Kelvin here. Like 10 degrees Celsius will be nothing but that is 283, right? So that is your T1 here. This is your pi 2 here. This is pi 1 here. This is T2 here. T2 is 25 degrees Celsius, right? So we know that T2 will come to this side, T1 will come to this side. As you can see this here, this will be pi of urea by pi of solution. This will be T2, this will be T1, this will be C of urea by C of solution. So put the values here and we will get that urea is equals to 5 into C of solution. That means the solution was diluted 5 times. 5 times the solution is diluted. 5 times with respect to the urea concentration. That is why the solution has, that is why the concentration of urea is 5 times. That means the concentration is decreased by 5 times, right? So that means you have diluted it by 5 times, right? So you can say the solution was diluted 5 times with respect to the urea solution. Okay, right everybody? So answer is 5 is the correct answer. Now this one is also, it may seem difficult, but it's not difficult here. I'll tell you what is the reason. Yes, everybody, do let me know. Let's see. Now it may seem tough, but it's easy question. You can do this easily. Let's see how. Let's see everybody how you can do this question. This is dry air is slowly passed through three solutions of different concentrations. So dry air is passed through this solution, then it will pass through this solution, then it will pass through this solution. Now what you observe here is, this concentration is C1, this is C2, and this is C3. Now if I see each containing non-volatile NaCl as the solute and water as the solvent. That means here the vapors, see, you are passing dry air and the pressure will be of dry air, right? As this, if the vessel 2 gains weight, vessel 3 loses weight, then what? First thing is, we'll talk about if vessel 2 gains weight. If vessel 2 is gaining weight, now always remember this one concept. The one that is losing weight has more pressure, and the pressure is more, it will have less concentration. It is based on this simple concept here, right? That when you have the one that is losing weight, so any vessel which is losing, which is giving off pressure, which is losing weight, that is going to have more pressure. That is why it is trying to decrease its pressure. And when the pressure is decreasing, the concentration will increase, right? Okay, yes, because the dilution, you can say it's kind of dilution that is decreasing, so concentration will increase in that case. Tell me which, if that concept is clear what we are saying, right? Now if I see vessel, we are saying vessel 2 gains weight. If this is gaining weight, this is losing weight, so you can write this here. If this is losing weight, then here pressure is more, that means concentration is less. So we can say C1 concentration is less than C2. Tell me, can I say that C1 concentration is less than C2, right? Why I am writing in the form of C1 and C2? Because if you see the options here, wait a minute, option should be here, right? These options, and here two answers are correct, right? Okay. Where have I written less concentration? Less concentration. I have written less concentration. Okay. So if I see this is gaining weight, that means this will be losing weight. Only then this is gaining weight, because the pressure is, because the air is coming from this side to this side. So if this is gaining weight, this is losing weight. If this is losing weight, that means pressure is high here, right? Pressure high means concentration is low here. So C1 has less concentration than C2. In the similar case here, what you will have, you have vessel 3 loses weight. Okay. If vessel 3 is losing weight, if this is losing weight here, that means here pressure is more. That means concentration is less. So you can say C2 concentration is more than C3. Okay? C2 is more than C1. C2 is more than C3. So B and D are going to be the correct answer here. So answer is B and D are the correct answer. Guys, tell me if that is clear to all of you or not. Right? Okay. Tell me guys if that is clear, because that was a different question, right? So that you can relate to this question, so that you can understand these things more deeply, right? Okay, everybody, do let me know if that is clear, right? Next question on your screen. Next question on your screen, everybody. We have Dry air was drawn through bulbs containing a solution of 40 grams of urea. You have 40 grams of urea and 300 gram of water. Then through bulb containing pure water at the same temperature, finally through a tube containing pumice moistened with strong H2SO4 was kept. The bulb, they are asking you osmotic pressure. Okay, they are asking you molecular weight of urea, right? Now this is actually based on a formula, that is the experimental formula, right, that I have taught you in the theory classes as well, right? So this formula also, very rare students go into that much depth of the chapter that they know this formula, right? So this formula is the experimental formula. Let me explain you that. It is relative lowering in vapor pressure is equals to, this is based on the formula, okay, based on the experiment. Relative lowering in vapor pressure is loss in weight of solvent or water bulbs, gain in weight of sulfuric acid. Just remember this formula as it is, right? So all these things will be given to you in the question. If you see, the water bulb lost is this grams, the sulfuric acid tube gained is this gram. This is a line that we were looking at. This is the direct formula from the experiment that you have. That is loss in weight in the solvent, gain in weight of sulfuric acid tube, that becomes relative lowering in vapor pressure. You put it here, you will have the value of relative lowering in the vapor pressure. Once you know this, then all you have to, they're asking you the molecular weight of urea, right? Molecular weight of urea. Wait a minute. Are they asking us molecular weight of urea here? Right? Dry air was drawn through this containing a solution 40 gram. And the weight of urea is given to you. Weight of solvent is given to you. Weight of solute is given to you. Right? Then through the bulb. Okay. Yes. So now if you relate it, if you write it here, we know that delta of P, or you can just write it here, relative lowering in vapor pressure is equals to number of moles of solute by number of moles of solvent. Number of moles of solute is W2 by M2. This is multiplied by W1, this is M1. Now, if you see this here, they are asking you molecular weight of urea from this. From this, you have to calculate. You can't directly say this is the molecular weight of urea, you have to calculate it from here, right? Because you can see the change here. It's not exactly 60, right? So that's why this M2 is what you have to calculate. W2 is given, W1 is given, M1 is given, water it is 18, right? You just put these values and you will get your answer. Mass of urea, mass of water is given to you, that is 40 and 300 grams. Wait a minute, this is mass of urea and this much of water. If you see, this is solute and this is solvent here, right? So overall molecular weight of solvent is 18, right? All these things are given to you. You put the values, calculate the value of M2 from there. This already you have calculated from this formula. That was the experimental formula, right? So what was tough in this question is this particular formula that most of the students don't know, right? That is the only thing here. Otherwise, so it is simple question only. From here, so it's simple only. This is a new part that might be some of you have come across this formula for the first time, right? Okay. Yes. Now let's see the next question here. That is, what is the osmotic pressure of 2.2 molar HX solution at this? Now see, Ka is given to you. They're asking you osmotic pressure. Pi is equals to ICRT. R is, we know, R is a universal gas constant. Temperature is given, concentration is given. Do I know the value of I here? No, ma'am. I know HX is dissociated to H positive and X negative. I know N is going to be 2 here. Whenever Ka is given, that means Ka means it does not have 100% dissociation. So I need to calculate the value of alpha, and if you know from ionic equilibrium, they ionic and solutions are quite related to each other, and this is how they ask you the mixed questions, right? And they are very important, right? If you see, this is not a tough question, but two things you have to apply here. First is Ka is equals to C alpha square for monoprotic acid. Alpha is equals to under root of Ka by C, right? Now Ka value you know, C value you know, you will calculate the value of alpha from here. That is going to be 8 into 10 raised to power minus 5 divided by 2 into 10 raised to power minus 1, right? And that is going to be 4 into 10 raised to power minus 4, right? That is going to be 4 into 10 raised to power minus 4. And once you have calculated this part, right? Once, guys, you have calculated, uh, ma'am, I couldn't understand why acetone and this could not be separate. I'll tell you that, dare to shine, don't worry, just give me a second. Right? Alpha is equals to under root of 4 into 10 raised to power minus 4. That will become 2 into 10 raised to power minus 2. Okay? That is the value of alpha. Now remember that this is 0.02. This is 0.02. Alpha is coming out to be 0.02. Now we should know that alpha is equals to 1 plus uh, n minus 1 into, oh yes, I is equals to 1 plus n minus 1 into alpha. N is what? How many atoms it is dissociating to? That is 1. So I is equals to 1 plus 2 minus 1 is 1. So it is going to be this. So you can calculate the value of I from here, put it here, put the value of concentration, put the value of R here. R you will put here as R value, remember that you put it as 0.0821. Whenever there is no energy, nothing involved, it's pressure and volume, when you put it as 0.0821, that is nothing but 1 by 12. Right? Okay. So put all the values here, calculate this. I is going to be 1.02 because alpha is coming out to be 0.02. Put it here, put the value of concentration, I, R, and temperature, and you will get your answer for Van Hoff factor. Right, everybody? Do let me know if that is clear. And your query, I'll answer it in the end, okay? Dare to shine, your query, I'll answer it in the end. Now let's talk about this thing, that is 5 moles of liquid X and 10 moles of Y make a solution having vapor pressure 70. The vapor pressure of pure X and pure Y respectively. Which of the following is true regarding the described solution? So if you see this over here, which of the following is true? You just have to tell whether P total is equals to P naught of X, mole fraction of X, plus P naught of Y, mole fraction of Y. If you see 5 moles of X is given, number of moles of X is 5, number of moles of Y is 10. So mole fraction of X is going to be 5 by 15. Mole fraction of Y is going to be 10 by 15. That is number of moles by total number of moles. Total number of moles is 5 plus 10, that is 15. Now, if you see, having a vapor pressure of 70, this make a solution. This is PT. Total vapor pressure of the solution is 70. Vapor pressure of pure X and pure Y. This is P naught, this is P naught X, this is P naught Y. Now you have all the values, you just have to find the relation here. Put the value of this as 70. This is, if this is coming out to be 70, this is what? This is P naught X is 63, this is 5 by 15, 5 by 15, right? This is plus P naught Y is 78, this is 10 by 15, right? Then calculate this and see if it is coming out to be greater than 70. If this is coming out to be, if this value is coming out to be greater than 70, that means it's positive deviation. If it is less than 70, it's negative deviation. If it is equals to 70, it's ideal solution, right? Okay, solution is positive or negative deviation, you just have to solve it. And after solving, what you will get here is, after solving, what you will get here is, wait a minute, what you will get here is that each term calculation, it is going to be 73 torr. After calculation, it is going to be 73 torr. Ma'am, why you have put 1 by 3 and this here, beta? Nothing, this they have just solved it. This is 1 by 3 na, 5 no, not 1 by 3, 5 3, yes, 5 3 1 by 3. This is 5 into 2 5 into 3, right? Okay, so that's how you have put the value. You can put here 5 by 3 and that also, right? So it is coming out to be 73 torr. That is obviously greater. So pressure is greater, that means we are talking about positive deviation here. So answer, wait a minute, P total is less. Okay, P total is less than, no, which is lower than the ideal pressure. This is observed or total? Wait a minute, let me see. This makes a solution of vapor pressure of this, the vapor, oh yes, PT observed is coming out to be, observed is coming out to be, that we have seen in the that we have seen through the experiment, that is 70, that is real. And PT, you can just say PT real is coming out to be 70. PT expected is coming out to be, expected is coming out to be 73. So from your expectation, you have lower value. You have calculated, when you only theoretically calculate, it's 73. But when you calculate it in reality, when you experiment it, it is 70. So your expectation has more value than the reality. So that means this is a case of negative deviation, where we were assuming something that they should be equal to 73, but that should be equal to 73, but actually it is coming out to be 70. That means vapor pressure has decreased. That means this is a case of negative deviation here, right? Okay, yes. So next question is Henry's law. Let's talk about Henry's law. Henry's law, constant KH of the three gases in water are these. The solubility of these gases in water will be what? Now see this. Now students, remember that solubility and Henry's law, how it is, Henry's constant, how it is connected. Solubility is inversely proportional to Henry's constant. Why? Because P is equals to KH into solubility. So if I say pressure is constant, then KH and solubility are constant. That means KH and solubility are inversely proportional to each other. So this is the thing that we have. Now more is the value of KH, less will be the solubility. So maximum value is for A, this is A, this is B, and this is C. Maximum value is of A, so it is going to have the minimum solubility. Minimum values of B, so it is maximum, then you will have C, then you will have A. This is the order of solubility, right? B, C, A, that is B is the correct answer here. Right, everybody? So answer is going to be B is the correct answer here. Right, everyone? Understood? Next question on your screen, what we have. Which amongst the following aqueous solution of electrolyte will have minimum elevation in boiling point? Let me see. There was one homework question as well. Wait a minute. That is there. Okay. Which amongst the following aqueous solution of electrolyte will have minimum elevation in boiling point? Now, what is minimum elevation? Delta TB is equals to I into molality into Kb. Right? Now, Kb is constant. What is different? I and this is different. Now alpha and all, it is not given, so that means I'll take alpha value as 1. Whenever alpha is not given or no way of calculation of alpha is also given, you will take it as 1. So whenever alpha is 1, you can say number of moles is equals to Van Hoff factor. So in this case, Van Hoff factor in all the cases, this is 2, I is equals to 2. In this case, I is equals to 2. In this case, I is equals to, this is 2 negative, this is 2 positive. So this is also I is equals to 2 here. Right here also I is equals to 2. That means I is also constant in all the cases. So delta TB only depends upon the molality here. It only depends upon the molality. So more is the molality, and they are assuming that if nothing is given, you can assume molality is equals to molarity, right? So we can say more is the molality, more is the delta TB, right? Minimum elevation, that means this delta has to be minimum, right? So you can say the value is, they both have same. This has maximum, minimum will be then this one, because this has lowest value of molality, so it is going to have lowest value of delta TB, right? Okay everybody, lowest value of molality, so it is going to have lowest value of delta TB. I value is constant in all these cases, right? You don't need to multiply this with Van Hoff factor because it is same only. So I have just seen molality, and that's how I got the answer. That is A is the correct answer here. Rest everybody. Now let's do the last question of today. Last question of today. That is, consider separate solution of 0.5 molar this of this, this of this, this of this. Which statement is true about solutions assuming all the salts are strong electrolytes? That means alpha is equals to 1, N is equals to Van Hoff factor, right? Now if you see, they are talking about osmotic pressure here, which has highest, same, highest, highest. So you have to find out the highest osmotic pressure. This is what they are asking. Pi is equals to ICRT. So if you see this here, R and temperature, all of them has 25 degrees Celsius. So temperature is constant. R is always constant. So you can say pi is directly proportional to I into C. So you'll have to calculate the value of I in all these cases. So I is what? This is alcohol, that is aqueous. So here Van Hoff factor will be 1 only because no dissociation will be there. This is 3, 4, 5. This is I is equals to 5. In this case, KBr I is equals to 2. K positive and Br negative. In this case, it is 3 Na positive. You can see 3 and overall here it is 1. So 3 plus 1 is 4. So I is equals to 4. Or you can write this like this as well. That here it is going to be 3 plus 1, that is 4. Right? Similarly here it was Mg 2 positive, that is 3. And this is PO4 3 negative, and how much amount? 2. So 3 plus 2 is 5. And here multiply this with the concentration. Okay? So for alcohol, calculated it is 0.5. For Mg wala, it will be 5 into this, so it will be 0.5, right? This will be for KBr, it is going to be 2 into this. 2 into this is again 5. Okay? 2 into 0.25 is nothing but 0.5, na? So this is into 4. So for Na3PO4, it is going to be 0.125 multiplied by, this is multiplied by 4. So 4 times if you put, that is also going to be 0.5, right? That means all of them are same. All of them has same osmotic pressure, right? So answer will be C is the correct answer. All of them has the same osmotic pressure. right? In these cases, all of them are having the same osmotic pressure. And that was your last question, guys. And this is your homework question, where which of the following, out of the following this much aqueous solution, which one will exhibit largest freezing point? Now, freezing point is directly proportional, is equals to I into M into Kf. Kf is same. You have to see which will exhibit largest freezing point. So molality is also same. That means delta Tf only depends upon the value of bond Hoffe factor, right? It only depends upon the value of bond Hoffe factor. You just calculate the bond Hoffe factor here. Bond Hoffe factor is equals to number of moles in which it is dissociated, and tell me which will be the correct answer. Answer should be written in the comment section over here. And one question that one of you were asking here, that was, let me see this over here. One question that one of you were asking, wait a minute. Ma'am, why non-ideal solutions? Ma'am, why they can't be separated by fractional distillation? See, whenever a solution is a non-ideal solution, what it will do, it will either be positive deviation or it will be either negative deviation. Positive deviation is minimum boiling azeotrope. Negative deviation is maximum boiling azeotrope. And if you see the definition of azeotrope, azeotropes are, they boil at constant temperature. Azeotropes means they will start boiling at a constant temperature. And for separation by fractional distillation, boiling point should be different. In the solution, both the components should have different boiling point. But for an azeotrope, they start boiling at a constant temperature. Now, both of them don't have separate boiling point. When the boiling point is not separate, then how can they be separated by fractional distillation? Okay. So that was the case, right? Okay, everybody, understood. And that's it for today. Now, before going ahead, right, let me tell you that the notes you will get for this particular PDF is over there in the description box. And also, guys, there is a rank booster test series that is right now available at just 999 rupees at totally 80% off over here, where you will get 11 part syllabus test, 25 full syllabus, and 3 hours each, right? This is total 36 tests that you are getting, 3 hours each, 75 questions, right? Just like the JEE pattern. And along with this, you are getting 93 high weightage topic tests. Like, for example, there is this colligative property, that is a high weightage topic. Based on that, once you have done that topic, you can just go through the test, and it will be 10 to 15 question in these 93 high weightage topic tests. So this is 25 plus 11, that is just 36 tests that are just like your JEE, right? And these 93 tests are 10 to 15 questions of each topic, that is high weightage topic, right? Okay. Yes, everybody. So that's it for today. Now I'll see you all in the next class, and that is tomorrow. And we are going to do chemical kinetics at 6 a.m. in the morning. So see you all tomorrow at 6 a.m. and do write your homework in the comment section. Till then, bye-bye and have a nice day. Have a great day, because you have started your day with studying, and that is a very, very positive thing that you have done. I'm super proud of you. And now go and utilize the full day with full potential. So all the best.